The purpose of this experiment is to determine the magnetic dipole moment through measuring the magnetic field of a bar magnet, as well as calculating the distance dependence of a magnetic field and comparing on and off axis magnetic fields. Major physics concepts include magnetic fields and dipoles, distance dependence, and the Biot-Savart law. Here I've also included the main results of my calculations and code. In order to set up the experiment, I had to download the app Teslameter, then align my phone with the North Pole, find the magnetometer chip location, and ensure that no outside metal objects were influencing my data. To find the on-axis magnetic field, I measured the distance between my phone and the magnet, which produced the given magnitudes in the x direction. I repeated this 3 times to get a reliable average and recorded the results in the Excel file. To find the off-axis magnetic field, I moved my phone a distance d perpendicular in the x and y directions to form a 45-degree angle between the magnet and my phone, as seen in the image to the right. I recorded these results from the app in the Excel file as well. These are the results found in my Excel file after inputting the information from Teslameter. In order to find mu of the magnet, which I later put into my code, I began with the given equation for the magnitude of the magnetic field of the bar magnet, and then solved for K, using the information from the populated graph that was in the Excel file as well, shown on the right. Once I found K, I was able to set the 2 given equations for the magnetic field equal to one another, and simplify it since the r's canceled out, and then solve for mu. The following function calculates magnetic field by taking in mu and r parameters, calculating the magnitude of r and r hat, and plugging these values into a coded version of the given magnetic field equation shown on the left. I then created on-axis observation locations on the x-axis and off-axis or perpendicular observation locations on the y and z axes, all the same distance from the origin in their respective directions. My code then uses these observation locations and the function I created to calculate magnetic field at each location, and creates arrow objects to visualize these. Lastly, I calculated the magnetic field using the same methodology at the location offset by 45 degrees. To do this, I input the average perpendicular d value from my experiment and used it to provide the r value that went into my magnetic field function. These are the results of my code. As a reminder, the orange arrows represent the magnetic field on axis, and the blue arrows represent the magnetic field off axis, while the green arrow represents the magnetic field at a 45-degree offset. If I hadn't oriented the experiment to compensate for magnetic north, my experiment and theoretical results would differ, and therefore my experiment would have overall provided inaccurate results. This is because the x component would not be isolated, and would also include the x component of the Earth's magnetic field, and therefore would be inflated. If I were to stick 2 identical magnets together end to end and run the experiment again, I would observe larger magnetic field values, and thus the observed distances would be larger as well. In conclusion, from the experiment, I saw that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Lastly, in this experiment, we were able to see the distance dependence relationship, in that as the magnetometer moved closer to the magnetic field increased.